Hi, everyone, and welcome to Compliance Panel's live webinar on Introduction to Design of Experiments and Analysis of Variance. My name is David Benjamin, and I'm going to be a host for today. And on behalf of Compliance Panel team, I would like to thank you for being part of this event. Now, today's webinar will be presented by Mr. Stephen Wallfish. Mr. Stephen Wallfish is the President of Statistical Outsourcing Services, a consulting company that provides statistical analysis and training to the FTA-regulated industries. And prior to starting Statistical Outsourcing Services, Mr. Wallfish was a Senior Manager Biostatics, Non-Clinical at Human Genome Sciences in Rockville, MD. Mr. Wallfish brings over 20 years of industrial expertise in the development and application of statistical methods for solving complex business issues, including data collection, analysis, and reporting. Mr. Wallfish has been an invited lecturer at Medical Design and Manufacturer, Institute of Validation Technology, and Advanced Star conferences. Mr. Wallfish has been a speaker at ASQ division and section conferences. He's also an editorial member, board member for Biofarm International, and a regular contributor to the magazine. Mr. Wallfish is a senior member of ASQ, a certified quality engineer and past chair of the Biomedical Division 2006 and 7. And Mr. Wallfish holds a Bachelor's of Arts in Statistics from the University of Buffalo, Masters of Science in Statistics from Rutgers University, and an Executive MBA from Boston University. We are honored to have such a distinguished person as Mr. Wallfish with us to present this event. Before we begin, I would like to inform you of the program outlined for this training session. The webinar is for 60 minutes duration. First, Stephen will take you through today's webinar, highlighting the areas that will be covered, and he will then share with you his presentation. We also request all to hold back your verbal questions until the Q&A window begins. 10 minutes of time will be allotted for the Q&A, during which you will be given an opportunity to ask your question verbally to our presenter. Now, if for any reason you get logged out of this training session or the teleconference, I request you to follow the same procedure to join in again. And now that we're all ready to start, I request Stephen to take it from here. Stephen?
Thank you very much, David, and welcome to everybody. I don't know if it's your morning or if it's your afternoon, but welcome nonetheless to the Introduction to Design of Experiments and Analysis of Variance. What we're going to cover today is we're going to start off by talking about the beginning of analysis of variance by talking about the one sample and two sample t-test. Then we'll talk a little bit about the different types of screening designs, fractional factorial designs you can do, as well as response surface. And then we're going to close with the analysis of variance. I ask if you have any questions and don't want to wait till the end to use the chat feature. And as I see the different questions that are coming up in the chat window, I will try to integrate them into the presentation along the way. And if you like, you can hold your questions till the end, and I'll be more than happy to answer them at that time. Okay, so understand, typically when we think about the analysis of statistical data, typically we work in the world of what is called the one sample t-test. And that is, we've collected some data, and we want to know if this data set that we've collected is statistically different than some hypothesized mean, and that's that letter mu, the Greek letter mu. And you use this t-test to say, okay, if my sample mean, which is that x with the bar on top of it, subtracted off my hypothesized mean divided by the standard deviation over the square root of n being the number of samples that I obtained in order to estimate the sample mean, I can calculate this, go to a t-table, and assume, or not assume, I can then verify if, in fact, my sample mean is statistically different than my population mean. And this works real well for comparing a single sample to a hypothesized mean. The extension of that is what is the two-sample t-test. And the two-sample t-test is basically where I want to compare two different means, or two different levels, or two different sets of data. And here again, you have x bar 1, x bar 2, and then instead of having just one standard deviation, you have the standard deviation of each of the different means. And so if we think about this for a minute, the one sample says I have a single set of data I want to compare to. The second, or the two sample, says if I have two sets of data. And what happens if I have more than two sets? What if I have three different levels? I have three different lots of material, and I want to compare lot 1 to lot 2 to lot 3. And that is where the analysis of variance will come into play. But before we get on to analysis of variance, what I want to do is cover with you is the idea of design of experiments, because I want to make sure that we understand how it is we're going to collect the different sets of data. So let's talk about the elements of a designed experiment. And as you'll see, typically you will see design of experiments broken into what I will consider to be two different schemes. The first being the screening experiment, and the second being the response surface experiment. And the screening experiment is a smaller set of experiments, not necessarily a smaller in the number of runs, but they're a smaller set in the total design space that we're going to evaluate, and you'll see what I'm talking about in a moment. And the idea or the purpose of these screening experiments is to identify the main effects. The main effects are those factors that contribute to the differences that I see in my response. The third thing is that screening experiments work only when we have a linear effect. That is, as the levels change, the response responds in a linear fashion. So if there's any sort of curvilinear or nonlinear relationship, these screening experiments are not going to capture that, because these are experiments that are run at two different levels. Factors are run at two levels. So you're going to have factor one. Let's just say I'm going to do an experiment, and this is if you ever did packaging testing. If you're going to make a pouch, we're going to make a pouch that we're going to put our either our tablets in if we're making a pharmaceutical, or we're going to put our medical device in if we're making a medical device. So we're going to make a pouch. And the pouch is going to be made on a sealing machine, and it has three parameters. It has the pressure, the temperature, and the dwell time. So those are my three factors. And each of those three factors I'm going to test at two different levels. So I'm going to have a low dwell time and a high dwell time, a low pressure and a high pressure, what is it? It's my dwell, and it's my so we have each of the factors at the two levels. So that is a typical screening experiment. Now, understand something about design of experiments. The response, the thing that we're going to measure, could be a quantitative number, so it could be the peel strength of that pouch, or it could be a qualitative thing such as pass or fail. And we're not going to talk a lot about what happens when your response is qualitative. What we want to concentrate on today, because it is an introduction, is to talk about when our response is quantitative. So what we want to do is we want to deal with quantitative responses and quantitative factors. The second type is this concept of a response surface experiment. And this is, if you can imagine, a three-dimensional picture of what the response looks like. Now, if we had just a linear response, that three-dimensional picture would be just a plane. It would just be a plane across the design space. But typically what happens is you don't just get a plane, you actually get some sort of picture. And imagine for a minute it looks like a little cowboy hat. That's a typical type of response surface you will see. In a response surface design, you're looking for interactions amongst factors, and I'll talk about what an interaction is. You're looking at setting factors at more than just two levels, typically at three or more levels, and this requires a larger set of experiments, larger set in the number of factor levels, in the number of runs, and usually in the cost involved in running these type of experiments. So when we talk about design of experiments, you can have smaller screening designs and bigger response surface designs. When we talk about screening designs, understand screening designs you'll sometimes hear are called fractional factorials. And then you will have full factorials and response surface. A fractional factorial is a design where I run a fraction of the total runs that would be expected to be run if I ran every single run condition. A full factorial, by its name, would mean I would run all of the possible run conditions that you can have. And then the response surface would be that experiment that looks at the shape of the curve. every design has something called design resolution. And this is important because when we do a design of experiments, and one of the things I want to sort of emphasize at this point is when I talk about, design of experiments and setting up different types of designs, the assumption I want people to understand is I'm not expecting that people are going to go back and design experiments on their own. Typically, what you will do is you will have software, and that can be, jump software, Minitab software, stack graphics, SPSS. There's a whole slew of different software packages available that can help you to design an experiment. And when you do that, this software is going to tell you what the resolution of the design is. So let's talk about each of the 4 different types of designs, resolutions. First is a resolution 3 design. In a resolution 3 design, it means that only the main effects can be estimated clear and free. A resolution 3 design means that the main effects are not confounded with other main effects. That means that if I see an effect for factor A, it is just due to factor A and not due to B or C. So this is where we talk about a design where we can estimate the main effects. But what is the penalty we pay for a resolution 3 design? In that case, one or more of the two-way interactions has to be assumed to be 0 because the two-way interactions are actually confounded with main effects. That means that when I said that factor A is significant, that means that the low level is statistically different than the high level. In order for me to assume that it is just due to factor A, I must assume that any of the interactions are not significant. And that is a big assumption. And if you cannot make that assumption, and sometimes you cannot, sometimes you know that interactions are going to happen, this is where you have to start to be more creative in how you set up your designs. And I don't want to spend a lot of time on that because I'm sort of limited to a 1-hour time period. But if you get yourself into that type of scenario where you know that you're going to have 2-factor interactions or higher that are going to be significant, I ask you contact me if you have a question specific to it, and I can try to address how to handle it. But typically what you will do is create another factor, which is just the interaction term, and we can talk about how that gets performed. A resolution 4 design means that the main effects are not confounded with each other, and they're not confounded with the 2-factor interaction. So now, when I see that factor A is significant, I know it's factor A because it's not any of the 2-factor interactions. They are able to be estimated on their own. However, 2-factor interactions can be confounded with each other. And this is a problem where, if you had an interaction between the A and the B factor, and we'll talk about what an interaction is in a moment. If there's an interaction between the A and the B factor, then I might say, oh, geez, I think that AB is significant, that interaction. But it also could be confounded with the C and D interaction, so it could be either AB or CD. So this is a problem you have to run into, is that you have to know which interactions you would expect to be significant and which ones you would not expect to be significant. A resolution 5 design means that there's no confounding between the main effects and the 2-factor interactions are clear and free. And then a resolution 6 or higher means that we basically can start to estimate 3-factor interactions. Now, before we get going on, I want to get a resolution 6 design, understand that as your resolution increases, the number of runs will also increase. That's your first thing you have to keep in mind. The second thing is that don't pay with more runs to get a resolution 6 design if you really don't care about 3-way interactions, and most people don't care about 3-way interactions. So in a screening design, typically those are resolution 3 designs. They're meant to find main effects. And a screening design's purpose is to basically take a massive number of factors and reduce it down into a trivial few that we really want to investigate. And we'll talk about that over the next half hour. Okay. So let's just understand the design resolution comparison. Let's take for a minute a design where I have 5 factors. And we'll call it factor A, factor B, factor C, factor D, and factor E. So I have 5 different factors, and that can be, again, the dwell time, the pressure, the operator. I mean, there could be 5 different things that we're interested in looking at. If I ran every one of the 2, and I set each of those 5 factors at 2 levels, if I ran every single run combination, there'd be 32 runs. And that is easy to calculate because it's just 2 to the 5th power. So 2 times 2 times 2 times 2 times 2 is 32. So there are 32 unique run combinations. So if I had a 5-factor study, each at 2 levels, and I wanted to run every possible combination, it would be 32 runs. And if I did that, that would give me a resolution 6 design. Now, I might not want to spend 32 runs in order to understand these 5 factors. So I might do something called a half factorial design, which is only 16 runs, and that only gets me down to a resolution 5 design. So that resolution that we spoke about becomes critical now. For half the number of runs, I'm only going from a resolution 6 to a resolution 5. And in most cases, a resolution 5 is a very good design anyway. So for 16 runs, I can get almost as much information as I would have gotten from 32. Now, even more of a factorial fraction of it is I can do a quarter factorial, or 8 runs. And this is a resolution 3 design. So typically, this is where I'd start out. If I was working on a project and we said we had 5 factors we want to look at, we don't know which ones are critical, I would suggest you run an 8-run design, a quarter factorial design, and we will figure out which one of those 5 runs, which one of those 5 factors in the 8 runs are significant. Now, typically, what I suggest here is to say if you have 5 factors, before you even run the experiment, before you do any of the 8 runs, you have to ask yourself one question, and that is, how many factors do I want to look for to be significant? Why is that important? Because you might not, because in a small experiment like this with only 8 runs, you might not find statistical significance, and you might be forced to stay and say, we're going to take the 3 most significant factors forward to the next set of runs. So before you get going, you want to know, am I reducing from 5 to 2 factors, from 5 to 3 factors? Am I only looking to go from 5 to 4 factors? Now imagine a situation where you have like 13 factors. If you have 13 factors, you're going to say, well, I want to go from 13 probably down to like between 3 and 5 factors. And I'm going to take the ones that are most significant. Now, remember, with 13 factors, I'm going at a much larger total number of runs down to a very small set. One of the things we want to do when we design an experiment is make sure that we have what is called an orthogonal design. And this allows factors to be measured independently of each other. One of the things that's very nice about most software is that they will give you an orthogonal design. Now, an orthogonal design, just to go back to give you from the past example, okay, 32 is the total number of runs. 16 was a half. A quarter factorial would be 8 runs. Someone might say, well, Stephen, I can only do 4 runs. Can I do a 1/8 factorial? Well, the answer would be no, because if you have 4 runs, but you're trying to estimate 5 things, what do you think happens? The main effects start to be confounded with each other. I have what is lower than a resolution 3 design. I do not have an orthogonal design. So that's one way you can lose orthogonality, is you can have less runs than you have factors. Another way you can lose orthogonality is instead of picking, and we'll talk about what it means to have a well-designed study in a minute, but you can pick your 8 runs to not be such that each factor has 4 runs at its low level and 4 at its high level. That's something you would desire in order to have orthogonality. So when I do a quarter factorial 8-run design with 5 factors, Each one of those 5 factors should have 4 of the runs at the high level, 4 of the runs at the low level. And we'll talk about how else we can check orthogonality in a moment there. So here is an example of a 3-factor design. And this comes actually out of Box Hunter and Hunter. And I want to concentrate on the left side there where you looked at the coded design. You have 8 total runs. So if I have 3 factors, each at 2 levels, 2 times 2 times 2 is 8 runs. So the 8 runs on the left side is the full factorial design. And if you look down, you will see that for factor A, factor B, and factor C, that in fact we have 4 negatives and 4 positives. Negatives being the low level, positives being the high level. As a matter of fact, you can look and say run 1 is when A is at its low level, B at a low level, C at a low level, and that is in the box that you see there in the lower left-hand corner. Run 4, for example, would be A at its high, B at its high, C at its low, which would be the upper right-hand corner. If you have 3-dimensional perspective, it would be the front of the box. And if you don't have 3-dimensional perspective, it's the number 1. It's the one with the number 4 on it. So that is a full factorial. I'm going to use this example, use this picture to now say, if you had to look at these, which 4 runs would I want to pick out of them if I wanted to do a half factorial? Well, do I pick any set of 4? No, I want to pick 4 such that I have 2 highs and 2 lows for each of the 4 factors. Each of the 3 factors. So which ones would it be? Well, let's see. If I did 1, 4, 5, and 8, would that work? 1, 4, 5, and 8. And if you look at those 4 runs, those 4 runs will give you 2 highs, 2 lows for each of them. So 1, 4, 5, 8. That means that 2, 3, 6, 7 would also give you the 4 runs. So those are the 2 sets of 4 runs that are orthogonal for this particular 3-factor design. Remember, I kept coming back. I talked about this word, an interaction. And an interaction is a very tough thing to conceptualize, so I'm going to show it to you with a picture. But an interaction, by definition, occurs when a relationship between 2 or more variables is modified by another variable. In other words, the relationship between the variables is different depending upon the level of each of the variables. As I said, it's very difficult in words. So let's look at this from a pictorial sense here. And you will see that we have a 3-factor study, and we have 8 different runs. And in the upper right corner, you have factor A. And what I did was I plotted the average of the 4 lows and the average of the 4 highs, and I drew a straight line between the 2. And as you can see, the response is lower at the low level of A and higher at the higher level of A. I did the same thing for factor level B. Again, I have the low 4 average of the 4 lows, the average of the 4 highs, and drew it. Again, it has that positive slope to it. So if you had to just look at those 2 pictures without any statistical mumbo-jumbo, one would say that I get a better response at the high level of A and a better response at the high level of B. But now let's look at the lower left box, and you see what is called an interaction. You can see that the lines actually cross. They interact with each other. And what you will see is that on the x-axis, we have factor A. And what each point there is now the average of 2 points. So if you have it in color, you would have a pink line and a blue line. If you don't have it in color, you will have a line that has a positive slope and one that has a negative slope. And the one with the positive slope, or the blue line, is when factor level B is at its high level, and the purple, or the pink or negative sloping line is where factor level B is at its low point. And this says, and remember, each of those 4 points, each one of those is an average of 2 points, right? So the positive sloping line has a factor level A at its low and its factor level B at its high. That would be the average of those 2 runs right there. So this says that if I am looking at the response is not just a function of A and B, but it's where I put A and where I put B. If I wanted to maximize the response, then I need to have factor level A at its high and factor level B at its high. If I wanted to minimize the response, I would have where? The minimal response actually happens when factor level A is at its high, but factor level B is at its low. So if I needed to minimize the response, whatever that response is, the truth is I would want to put factor level A at its high level and factor level B at its low level. So the interaction tells an awful lot about the way one should conclude. Now, remember what I said early on. Typically, when we are doing screening designs, we assume that there are no interactions. And this is a problem that we must deal with on a regular basis, because if this is a true situation and I'm assuming the interaction is not significant, I would probably conclude to run A at its high level and B at its high level. And if I did that, I would probably, to get a maximum response. But if I wanted to get a minimal response, I would have put A at its low level and B at its low level, which would have gotten me actually the top of the negative sloping one. It would have actually gotten me a very poor response. And let me just show you. This is the data point that I'm talking about right there. That's B at its low and A at its low. And it actually, if I was trying to minimize the response, of the 4 possible places I could have set the 2 factors, it gives me the second, it gives me the second worst place to put it. So as you can see, it's very important to understand the concepts of interactions. Okay. So how do you select the best design? What I mean by how do you select the best design, I want you to kind of think about, if I'm going to run a 3-factor study and I want to only run 4 runs, how do I know which 4 runs to choose? And how do I actually go about doing that? Well, a couple of points to keep in mind. First and most important is to randomize the run orders in order to distribute the random error over the entire experiment. Do not run negative, 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 positive, 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 negative, so that you run your 2 negatives for factor A and then you put 2 positives. You want to randomize the order of the runs so that there is no order in which the positives and negatives come. That's the first and foremost, most important thing you can do in design of experiments is to randomize. The second thing is, when doing a fractional factorial, you need to be very careful to design and assign factors such as A and B to control for interactions that are under consideration for analysis. Just using a very simplistic example of 3 factors, factor of A, B, and C. And if I did that half factorial 4 runs, the A factor is going to be confounded, or it's going to be co-estimated with the BC interaction. So if I see that A is significant, it's either A is significant or the BC interaction is significant. The B would be with the AC interaction and the C would be with the AB interaction. So you want to make sure that what you call factor A, factor B, and factor C is aligned such that one makes sure that the interaction that's confounded with it is well understood. In a 3-factor, it's hard to do because it doesn't necessarily work out that way. When doing a fractional factorial, interactions that are not tested directly are assumed to be negligible. And this isn't an underlying assumption. later on when you do a response surface design, you can actually test the assumption of the interaction. The problem you're going to run into is you might conclude during the screening design that a certain factor should be eliminated from consideration, when in fact it actually would have been significant, but one of the interactions that was confounded with it hid that significance. That happens, and in what I call statistical parlance, it's just tough luck. There is no way to be assured unless you want to spend the money to do a lot of runs. And a lot of companies now are trying to cut expenses and trying to get designs and get products to market faster, and that's why you do design of experiments, to minimize the number of experiments, to get products to market faster, to reduce costs. All those things put together, you're going to take on some risk. And the last thing is, you got to make a decision. Should you spend more runs identifying main effects or interactions? I will tell you, if anyone ever calls me and says, Stephen, I want you to come help us design experiments, work with our, the company, I'm going to tell you, spend all of your time and effort in understanding the interactions at the tail end of the experiment. So in other words, if we're going to sit and brainstorm out 13 or 15 or 20 different factors, I'm going to go through and say, let's get it down to 3 or 5 different factors. I'm not going to worry about spending a lot of money up front to understand the interactions amongst the 20 factors, because I have a very simple theory on design of experiments. If a factor is truly significant, it will show itself off. If a factor truly is significant, it's going to be the effect will be much larger than any of the interactions that it's confounded with. So if you truly have a good factor, it will show up. If it's a marginal one, it might not show up, and you know what? I don't want to spend a lot of time and effort understanding that particular factor. So typically, spend your money on the response surface and the later designs. Spend less money on the screening designs, because truthfully, that's where you make your biggest bang for the buck. Okay. One of the things I keep saying is I use the word confounding. You might also hear a term called aliasing. So aliasing, confounding, one and the same. Here is an example of how aliasing occurs in a particular design. In experimental design, when 2 interactions or a main effect and an interaction share the same column and cannot be individually analyzed, their effects are called aliased. Okay, so here is a design with 3 factors, and you will see that this is a half factorial. It's 4 runs. I've got 2 negatives, 2 positives for each of the 3 factors, and if I multiply together the column A and column B, I'm going to get that last column called the AB interaction. So negative 1 times negative 1 is positive 1, positive 1 times negative 1 is negative 1, negative times positive is negative, and the 2 positives is positive. If I look at the AB interaction, which one of the 3 columns does it look like? It looks exactly like factor C. So factor C and the AB interaction are aliased and or they are confounded with each other. So this is how you can understand the confounding patterns. You can multiply through any 2 columns, and if the resultant column is exactly the same as one of your factors, then they are confounded. In some experiments, we need to do something called blocking. And blocking is a method by which we are able to account for different sources of variability that just happen to occur during our experiment. The most common thing you block on is days. You have a design. You're going to have to run 16 runs. You can only do 4 runs a day. Then you must run 4 runs on each of the 4 days for your 16 runs. You block on the day, and you make sure that each of the 4 runs on each of the 4 days has 2 highs and 2 lows for all of your factors. That remains and allows you to distribute over the blocks the runs such that you can now look at the highs versus the lows for a given factor, and then also look to make sure that the day-to-day variability is not large enough that you are biasing or in some way influencing your analysis. And as I said, you want to typically block on things like days, operators, and incubators. What do you do when an interaction is significant, though? If an interaction is significant, and we're going to call something significant when the p-value is less than 0.05, there are three scenarios to deal with. The first is when both the main effects are significant. So if the A-B interaction is significant and both A and B are significant, well, we can then deal with this because we can set A and B at the right levels such that we can minimize the effect of the interaction. What do you do if only one main effect is significant? Then you can plot that interaction plot that you saw I had a couple of slides back and set the main effect levels such to minimize the interaction, controlling for the significant effect. This is the best scenario because if only one of the two factors is significant, you can find out where the interaction is. It doesn't matter where you set that other the second factor because it's not going to have any impact on the response. And it allows us to be able to find the optimal place to be. If neither the main effect is significant, but the interaction is, this is a situation where you kind of get yourself, scratching your head going, what do we do? And I usually say this is a case where you have basically said that factor A and factor B by themselves, not important. Create a new factor called AB and run all future experiments. So you're now basically setting the levels of two factors, but you're doing it in combination. So you're going to create an experiment where instead of having high and low, you're basically going to have A and B at its high and A and B at its low, or some combination thereof, but basically finding the combination of the interaction to control in the experiment. And you have to, this is unfortunate with a webinar, it's a little bit more difficult to conceptualize, but imagine if we went back to that picture I had a couple of slides back over here. One might say that I'm going to create a new factor and I'm going to run A at its low and B at its high, and then I'm also going to have a factor where A is at its high and B is at its low, and create that as my new factor along the way. Just talk quickly about a little bit more about screening designs and when you use them. Typically, they're done early in development, and it's desirable to identify the critical few from the trivial many factors under the study. Screening designs look at the main effects only. One of the most common screening designs you'll see is something called the Plackett-Berman design. And the beauty of a Plackett-Berman design is it allows you to study n factors in n+1 runs. So the most common one that you'll see is people will look at 11 factors in 12 runs. And Plackett-Berman designs start at 12 runs, and they go up by 4. So there's a 12-run Plackett-Berman, a 16-run, a 20-run, 24-run. If you want to do a 24-run Plackett-Berman, you can look at 23 different factors. That's a lot of factors that you can evaluate very quickly, or relatively quickly. So one of the beauties of Plackett-Berman is that it allows you to look at n factors in n+1 runs. The next type is something called a two-level factorial design. This is what we spoke about. A full factorial will be 2 to the k, where k is the number of factors in the study. And a fractional factorial is 2 to the k minus q, where q is a positive integer that is less than k that indicates the fraction of the study. So if I had a 6-factor study, a half factorial would be 6 minus 1. A quarter factorial would be 6 minus 2. An eighth is 6 minus 3. 16th is 6 minus 4. So 2 to 6 minus 4 would just be 4 runs. So instead of doing 64 runs, I'm only doing 4 runs. Quite a highly fractionated design. One of the things is that understand that fractional factorials are very intuitive things. For example, if you want to study 7 factors, you would have to run 128 runs. So you're not going to do that because no company is going to chalk up the money to give you 128 runs just to look at 7 factors. I should say no. Most companies I know would not do that. So you will definitely do a fractional factorial and sacrifice interaction effects so that the main effects can be computed and evaluated correctly. Again, here is that design that you saw before. 8 runs, 2 levels, 3 factors, and we can go and look at some of the interactions. We can look at all the two-way interactions. So this particular design, in 8 runs, I can look at the 3 main effects, and I can look at the 3 2-factor interactions. I can also, if I wanted to, look at the 1 3-way interaction. I will tell you, and we will talk about this a little bit more in a couple of slides, it is imperative not to get yourself caught up in understanding high-level interactions. 3-factor, 4-factor, 5-factor interactions are meaningless things. It's great to theoretically do it and say, oh, I can estimate a 4-factor interaction, and maybe you can. But how do you actually control if you understand that this 4-factor interaction is significant? It is important to understand from a statistician's perspective that not only do we want to be able to estimate with ANOVA, which we'll talk about in about a minute, but we also want to be able to control a process based on those results. Again, some of the screening designs that you'll see here, Plackett-Berman, fractional factorial, and then you might see this thing called a Taguchi type experiment. These are highly saturated designs where you are looking at signal to noise and not looking at p-values. Again, I put it in this presentation for you. If it's something you're interested in, feel free to contact me, and I'll be more than happy to provide some additional information on Taguchi type of designs. Oop, come on. It's not wanting to advance. Okay, well, the next slide is an example of a Plackett-Berman design, and unfortunately, I don't know if you're seeing the slides, but they're not. The slides are not up.
Steven, I can see the 27th slide.
Do you see the slide 27?
Introduction to ANOVA, yeah.
Okay. Let me. It did not update. I'm still seeing slide 21. So. Now all my slides are there. So everyone else, I'm assuming everyone else is slide 27. Is that true, David?
Yes, introduction to ANOVA. We're on 27th slide.
Okay. I'm going to do this. I'm going to give myself.
You finished the 25th.
Okay. I'm going to try to advance it. So, you know, as I talked about the Plackett-Berman, it's there to screen. It runs in multiples of 4. Okay. So in the introduction to analysis of variance, let me just see why I'm not. Well, all right. So in the introduction to ANOVA, when a factor has more than 2 levels, the t-test that we talked about at the beginning is no longer an effective analysis method. We need a method that can simultaneously compare all the factor levels for statistical differences. And in this case, we use what is called analysis of variance, which gives us a null hypothesis that all treatment levels are equal. So what we're testing in ANOVA is not if level 1 is different than level 2, or if level 1 is different than level 3. What we're saying is if I have more than 2 levels, I'm testing a hypothesis that basically says is any one of the two, any set of 2 factors, are they significant? So that is the idea of ANOVA. So what I use the word ANOVA, and just to kind of give you a feel for what ANOVA is, ANOVA means analysis of variance. And one of the kind of misnomers about ANOVA is that it actually is comparing means, and that's not what's happening. Analysis of variance works very simply. It says that I can look at variability between factor levels, means, and compare it to the variability within a factor level mean. And if the variability amongst the means is greater than what I would expect to see within a factor level, then I would call those differences. We say it differently. And we'll see this in a minute when I show you the ANOVA table. But the way that analysis of variance works is it says I can look at the variability among the factor level means. And if that variability is larger than the average variability I see within a factor level, then in fact I have a significant effect. So if we want to use analysis of variance for doing validation, that's typically what you'll see a lot of people like to do. They like to use DOE for doing validation. In that case, a null hypothesis is no statistical difference. So this is a generic ANOVA table. And you'll see that it looks at, from the bottom up, the model variability, the error variability, and the total. The model is that variability among the level means. The error is the average variability within a level mean, and the total is the sum of both of those. And the F ratio is the comparison of the model to the error. And we take this F ratio and we compare it to a table of F values where we have the numerated degrees of freedom, which is the model, which is n minus 1, the number of levels minus 1. And then you have the error, which is n, which is the number of levels, n is the number of replicates, times a minus 1, which is the number of levels minus 1. And that, you go to an F table and you compare what you get as your F ratio and compare that back to the table value, you compare it to what you observe, and if it's bigger, you call that statistically different. And let's take a look at what that would mean in a real live ANOVA. So this is an analysis of variance where I have 2 degrees of freedom, so I have 3 different levels for my model. I have an error, which is 6 degrees of freedom. So that means I have 3 replicates at each of those 3 levels. Therefore, I have 9 total observations. And when I go through and do the F ratio, which in this case would have been the 8.43 divided by 7.31, I get 1.15. I take that to the table value for 2 degrees of numerator degrees of freedom, 6 degrees of denominator, the value would have been 5.14. So if the F ratio would have been greater than 5.14, I would have concluded that there's statistical differences amongst the levels. But since the 1.15 is less than 5.14, I conclude that, in fact, there are not statistical differences amongst the levels. Okay. The next piece is the idea of a mean squared error, or the mean squared. So if I go back up to the previous one, you see the MS column. The MS column is the mean squared, and that is the average squared differences amongst the values. But the one thing I want to I want you to focus on is what is called the MSE, or the mean squared error. This is the inherent variability of repeat readings across all concentration levels. It is what is considered to be the within-run variability. It is an important estimate because it gives me the average variability I would expect to see if I took the same run conditions and continually ran those runs. That's the variability I would expect to see amongst my responses. So the mean squared error is the inherent variability of the repeat readings across all concentration levels. So let's take a quick peek into an example here, and then we'll talk about a couple of multiple comparison tests, and then we'll open it up for questions. If I have a design with 4 different runs, each with 4 vials, that's 16 total observations. I have 4 different runs. Each of the 4 runs is 4 vials. I want to measure the percent moisture in each of those vials, and I want to see if there's any run-to-run differences. These are 4 lyophilization runs. We're going to measure percent moisture in 4 vials in each of the 4 runs. Okay, and so that takes us to this particular set of data. On the left table are the 16 different observations. So run 1 has a 1.93, 2.38, a 2.20, and a 2.25. Run 4, 2.33, 2.40, 2.28, and 2.25. So I can now do analysis of variance, and since I have 4 runs, I have 3 degrees of freedom. I have A minus 1, the number of runs, minus 1 degrees of freedom. I do this in software. I'm not giving you the formulas to calculate the sums of squares and mean squares. But you take the sums of squares, you divide it by the degrees of freedom, that gives you a mean squared. If I take the 0.1734 divided by 0.0203, I get a F ratio of 8.54. When I go to a F table for 3 degrees of numerator degrees of freedom, 12 denominator degrees of freedom, I find out that the p-value is 0.0026. Since that's less than 0.05, I conclude that one of the runs, at least one of the runs, is different than the other runs. So not all 4 runs are identical. One of the runs is different. So that brings me to a bit of a problem. How do I know which run is the one that's different? Typically, this is what most people would do. They would go and say, well, I'll just do a bunch of t-tests. I'll compare 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, 3 to 4. And when I do that, I would say, oh, well, 1's different than 2, and 2's different than 3, and 2's different than 4, but 1 and 3, 1 and 4, and 3 and 4 are not statistically different because the t-tests show me that a p-value is greater than 0.05, so they're not statistically different. Is that in fact the case? Well, in analysis of variance, there are a set of multiple comparison tests that one can do to look at the different types of comparisons. One is called t-test, one Tukey's, one is called student Newman-Coles, and another is Dunnett's. Dunnett's compares each of the runs back to a control. The t-test I just showed you, Tukey's and student Newman-Coles are 2 other types. What I'm going to do is, because we're coming up against the time, I'm just going to give you a quick overview of each of the 4. The Fisher's protected t-test, or the t-test, says that after the ANOVA shows a significant difference, then and only then could you do the t-test. This is it's the weakest of the multiple comparison tests, and it is usually not done as a way of doing multiple comparisons. A more likely one is something called Tukey's honestly significant difference. This allows you to look at all of the differences amongst the pairs, but it controls for the fact of the number of comparisons that you're going to do. And typically, this is the one you will see in most software. If you use JUMP software, they have Tukey's HSD test, and this tells you which set of means are different. Then the last one that we'll talk about is the student Newman-Coles test. This is my personal favorite. This allows you to look at not only sets of 2, but allows you to look at sets of 3 and sets of 4 and all the way up. two subsets to be able to look at the factor level means. And as I said, the last one being Dunnett's, which compares you back to a mean, back to a control. This would be typically if you were doing a study where what you're doing is you say, I've got an existing process. I want to know if my new process is better than that. So one of your run conditions is going to be, one of your levels is going to be the existing, and I might look at 2, 3, or 4 different types of changes to the process. And all I care about is my change in the process different than my run conditions that I ran at the present time? So with that in mind, we are pretty much out of time, and which is just as well because we're at the end of the slides. And so I'd like to ask if anyone has any questions. David, if you can open up the lines for questions, or if you want to do it via the chat. Either way, we can answer questions. And I apologize for some of the technical difficulties that we had towards the end there.
Stephen, thank you very much for the wonderful presentation, and also all the participants for cooperating with us. It is time for the Q&A to begin, and we request all who have questions for a presenter to click on the raise hand button, which is a palm-like icon at the bottom of the participants panel to ask your questions verbally, or you can post your questions on the Q&A panel so that our presenter can read it aloud and answer. Stephen, I think most of them are logged out of the training session. May I unmute the lines one by one and ask them if they have any questions? Will that be okay?
Yes, sure.
Elaine? Elaine, can you hear me?
Thank you. Could you provide some other references?
You want some reference books?
Right.
Okay.
Or papers?
Here's a couple of books I think when you want to learn about DOE that'll take you through different stages. The one that most people are familiar with is the Box Hunter and Hunter book. And as I'm looking here in my office, I'm trying to find my copy of Box Hunter and Hunter, and it's called Statistics for Experimenters. And it is really the standard by which most people look. Another book that I find very handy is something called Fundamental Concepts in Design of Experiments by Charles Hicks, H-I-C-K-S. Another really good DOE book. And there's a whole bunch now that are out that you'll see that go under the guise of like Design for Six Sigma. I'm not familiar with a lot of them, but there are a whole set of those books available that can kind of give you some guidance for picking a design.
Oh, thank you.
Does that help you?
Yes.
Okay, thank you.
Thanks.
Thank you, Stephen. Lindsay. Lindsay Sokol, any
Hello?
questions?
Hello.
Hello? Is that me?
Wendy. Yes,
Oh,
Wendy.
yeah, Wendy. Yes, I have a couple of questions. First, thank you very much, Stephen. It's a very good talk.
Welcome. Thank you.
And the first question I have is like often you talk at the beginning that today's seminar just for the variables or response that is continuous quantitative ones. So I do have some of those qualitative response or variables which have different levels of response to those. So apparently I can use ANOVA instead. I may use those categorical or chi-square kind of analysis.
So that's an excellent point. So if you had a response that is categorical in nature, you can do a contingency table type of approach and do a chi-squared. So you would have, factor levels, and you count the number that you would have. That's one of the most common ways to do it. Another way that people have done it is something called logistic regression.
Yeah.
That gives you a odds ratio of one level over another. Either one of those are fine to use.
Yeah, but in terms of experiment design-wise, like in terms of data analysis part, it seems straightforward. Can use those kind of tools. But in terms of the experiment design, what do you think? Should still use the same concept?
Yes. So the response only affects how we analyze the data. But if you wanted to do, you would use a typical same design of experiments, but instead of response being pH or being percent moisture, it's going to be, you know, like it, don't like it, might like it, you know. That's how we analyze the responses, you know, is how we analyze the data. But the design of experiment doesn't change. And really, if you think about it, I mean, it's just the way survey designs are done. Survey designs are done, well-designed experiments, but they're analyzed differently.
Yeah, I think the questions here say you can have the different level of design or the runs, and that part is clear from your talk.
Oh, okay.
And how about the number of samples? So, for example, the runs in the quantitative case, you can see around the number of repetition for each experiment, this many. But for the categorical data wise, under one condition, how many samples you should collect? Is that clear?
That's an excellent question, Lindsay. And I don't have a real good answer to it, because you actually have to look at doing power analysis. You have to look at how many different categories. So if a response is a binary, it's either yes or no, present or not present. The number of samples you need to take it for each run is a lot less than if you had 5 different levels. And I'm going to say, typically, the way that I have done it is I use it's called a factor of 5. So if I have 5 different categories that I can go in, then I need to have a minimum of 25 responses per run.
Okay, minimum.
Because,
I'm sorry, go ahead. Yeah.
Because typically the problem is that the chi-squared value is unreliable when the expected number of responses is less than 5 in a particular cell. So typically you want to try to get at least 5 responses in each cell. And so in order to do that, you need a minimum of 5 times the number of cells you're going to have for a particular run. So that's why I say the factor of 5, and that tends to work pretty well. You might get some cells with 3 or 2, but it's the best you're going to do.
Yeah, in the one place in the statistical book, where they suggest it's all like they said it depends on the frequency of yes or no. Like if it's to a level of response, depends on frequency. If the probability of that one particular response is not in the middle, for example, it's 0.1 or 0.2. In that case, then you'd better to have the sample size bigger than the certain number, so that the sample size times the probability is bigger than 5.
That's correct, and that's what I'm saying. So it's not a straightforward answer. That's why I tend to use 5, assuming that if I had 5 different levels, that each one had a 0.2% chance of being there. But if one of them has a 1% chance, then you're going to have to take, you know, a minimum of 50.
That's right. For that particular cell, is that right?
Yeah.
I see. Okay. So that's okay. So basically, that's the part I'm struggling with. I think that's.
And so here's the thing. So to kind of so everyone understand, if you have again a situation where you have 5 levels and one of those levels only has a 1% chance of being selected, it's not really a level, and don't even just take it out of the study. It's not a category that's worth investigating. So just remember, what you're really trying to do is to say, is category 1 different than 2, then 3, then 4, then 5? And if that's what I'm really looking at, and one of them truly has a very low probability, I know that it's going to be different. So there's not a lot from a DOE perspective to do. Now, you might include it in there because you need to, you know, it's a category that has to be there. But I wouldn't increase my sample size to capture a minimum of 5 there, because I know it's going to be different. So, I mean, I know my p-value is going to be small. That's the point I was getting at.
Okay.
Does that make sense?
Yeah.
From a DOE perspective.
Okay. Yeah. I don't want to take too much of your time. So another question is like I'm using R software. And do you think it has an experiment design part? You mentioned all the other commercial software.
So the problem with R, you know, first of all, if you could do programming in R, you know, you're well ahead of most of the people. I don't believe R has a DOE module, you know, because it's a coding. But I can look into, you know, if you have my email address, if you send me an email, I'll be more than happy to look into if there's a site, if someone wrote an application to do DOE. I don't believe so. I believe they probably did for the analysis of the designs, but not the actual creation of a design.
Okay. Yeah. So it does not have that. Oh, okay. I don't know. I'm just okay.
Yeah, I don't believe it does. That's the I don't believe it does have the ability to do design experiments.
Okay, great. Thank you very much.
Thanks a lot.
Thank you, Stephen, for the answers. And Douglas, do you have any questions? Mr. Douglas Frost? And Stephen, I don't think there are any more questions. With your permission, Douglas.
Okay.
Thank you very much, Douglas. He said there aren't any questions. And with your permission, could we conclude the session, Stephen?
Yeah. So if there's good.
I'm sorry. May I ask one more question? Yeah. Those slides you showed, are they available to us?
Well, yeah, I've sent it to you along with the invitation mail I sent.
I never received it. I'm sorry.
All right. I'll resend it to you again soon after the session.
Oh, okay. So you will send the slide to me. Okay.
Yeah.
Great. Thanks.
You know, Lindley, if you have, if you want, you could send me an email at steven@statistical-outsourcing-services.com.
Okay.
And I'll be more than happy to answer any of the questions that you have.
Oh, great. Thank you so much. I will. Yeah.
Okay. All right, David. Thank you very much. I want to thank everyone who's stuck in with us, and look forward to seeing you on a future webinar.
Thank you.
And ladies and gentlemen, we're very thankful for your participation today. And if you'd like to get in touch with us, you can send us an email at webinars@compliancepanel.com. And if any of you feel your colleagues, team members might benefit from this event, we are happy to inform that it will be available in the recorded format and can be purchased from our website. Or you can call us at 714-441-5856. We welcome your suggestions and feedback or ideas on how we can improve our webinars. If you'd like to suggest a topic or desire a customized corporate training online or on-site, we ensure that whatever is your training necessity, it will be our priority. We look forward to having you with us again sometime soon and for your continued patronage. On behalf of our presenter, Mr. Walfish, and the Compliance Panel team, I would like to say thank you for participating in this event and wish you all a pleasant day ahead.
Thank you.
Thank you very much.
Thanks.